In this video, we'll look at electron affinity. Electron affinity is energy. It's kind of like ionization energy. Sometimes it's referred to as electron affinity energy. It's actually the opposite of ionization energy. Electron affinity is the energy change that happens when an atom gains an electron. So if I wanted to break this as kind of like a little equation, it might be my atom X, whatever X might be, and X is going to gain an electron. And by gaining an electron, I form the X minus 1 ion. I'm not changing the nucleus, but I'm gaining an extra electron. And when that happens, when I gain an electron, if it means that I gained an electron in a way that makes the atom more stable, maybe I filled my outer shell, now energy will be released. So we'd say plus electron affinity energy. Electron affinity energy. So they're kind of opposites. This electron affinity is energy released, so it's on the product side, it's produced when I gain an electron. But on the flip side, if I go back a little bit, whoa baby, we did a lot of work. If I go back to ionization energy, it was energy I had to add to remove an electron. And when I remove an electron, I form the positive ion. Now we're on the other side of town. We're gaining electrons to form negative ions. And so if you look at some of these numbers on this little periodic table, again, the numbers are usually in units of kilojoules, and we don't really care so much about the exact number. I just want to look for trends and patterns. And so, for example, in general, electron affinity energy seems to increase going across a period. And by increase, it means that it becomes like more exothermic. So, like for example, fluorine. When you see here that fluorine is negative 328, it really means like 328, usually units of kilojoules of energy are released. And we'll talk about energy a lot more second semester, but in general, whenever you have a negative energy value, it's just indicating that that's energy being released. A positive energy value would mean that it's energy being absorbed. And so, again, I don't care so much about like the negative. This is all, I mean, anytime you see a number, it's referring to energy released. That's kind of the key here with electron affinity. It's energy produced. And so we're just looking for the greatest, maybe numerical values. Where do I find some of the largest electron affinity energies? And in fact, it kind of seems like as I go across, they seem to, in general, increase. I mean, if I think like sodium and I get like, okay, magnesium's almost 0. Weird. And then, you know, okay, aluminum and sodium are kind of similar. But then as I go from aluminum to silicon, phosphorus, sulfur, chlorine, they all tend to increase, which just means they're releasing more and more and more energy. And then I end with argon. In general, all the noble gases are about 0. That's kind of weird. Okay, so let's see what this really means. We're talking about gaining electrons. And in this, like number 16 question, they have a picture of a fluorine atom. And if I think about like the electron configuration or the orbital diagram of fluorine, fluorine should have 7 valence electrons, or a total of 9. But if I do the fluorine electron configuration, it's like 1s, then there'll be the 2s, then there'll be the 2p's, and I've got 1, 2, 3, 4, 5, 6, 7. Sorry. 8, 9. Somebody's got to be paired. Okay, so again, this is my core. These are my valence, all the electrons in my highest energy level, which is the second. So these are all my valence. 9 total electrons, 7 valence. Okay, well, our goal here is to make this atom more stable by filling its outer energy level. And so right now, do you see what's going on right here? We're close. We've just got one hole. There's one more spot in a 2p orbital where we could gain an electron. And if we do, bazinga, we've got a full outer shell. That makes the atom stable. We could fill that second energy level by just gaining one electron. But that seems pretty reasonable, right? And now also think about like the fluorine atom in general. I mean, the fluorine atom is a pretty small atom. And so, I mean, all the halogens are going to be kind of in the same boat in that they all have 7 valence electrons, and they just want to gain one more to get 8. So they're very likely to gain electrons. And fluorine's a small atom with lots of attraction. So yeah, fluorine's going to want to gain one more electron. Fill that outer orbital. And so really when you look at these groups going across, almost all of them, for I should say the period going across, almost every row will have the halogen showing the highest release of energy, the highest electron affinity energy. Well, and if you think about it, then like every time you go across the period, the attraction is supposed to increase. We're adding another proton to the nucleus. And even though, yeah, we're adding electrons going across, they're all going in the same energy level. They're just filling the second level or filling the third level. But that nucleus becomes more and more positive. And so the attraction increases. I'm going to make a little note of that. As I go across, the attraction keeps increasing. Attraction increases. And so that attraction increases not only within its own atom, but the attraction also increases then for maybe neighboring electrons. Yeah, we want to gain electrons, and especially in this non-metal region. I'm like, these guys are all my non-metals. This is the part of the periodic table where you've already got like 4 valence electrons. Like everybody in the carbon family has 4 valence electrons. Everybody in the nitrogen family has 5, 6, 7 valence electrons. So we're close to that full outer shell of 8. It's easier just to gain a few and form that negative ion. Whereas these guys, like here, everybody in the first group only has 1 valence electron. Here in the second group, there's only 2 valence electrons. Or the boron family, there's only 3. Well, those are all metals, and metals only have maybe 1, 2, 3 valence electrons, so they're more likely to lose those few and form a positive ion. But here in this area of the periodic table, the nonmetals that already have close to an octet, close to a full shell of 8, it's more likely that we gain electrons. So that's usually where you're going to see the higher electron affinity energies, and they're going to be really low with metals. And so like your alkali metals, alkaline earth metals, they even left the middle transition metal group out. That's that gray part in the middle. But they're all really low because those atoms are not likely to gain electrons anyways. And then, yeah, so when I get to my nonmetals, that's where I find the highest electron affinities, just because they're more likely to gain that electron. Like, we just need one more electron right there. And then we fill that outer energy level, And so as the attraction gets stronger going across a group, it's more likely that we'll gain the electron. And when we gain the electron and form something stable, energy will be released. We have to add energy to break things apart. So when I wanted to remove the electron, then I have to add energy. It's attracted to the nucleus. But now here, when I gain the electron and form something more stable means low energy. So we're going to release that energy, probably in the form of heat or light. So in number 16, we're supposed to develop and use models. They gave us a model of a fluorine atom. They want us to draw a model of neon. Why do the noble gases have relatively low electron affinity energies, or electron affinities? Use the model of fluorine and neon as evidence to support your answer. Okay, so yeah, I mean, you're gaining electrons going across the group, and you get this really high amount of energy released when you hit the halogens in pink, and then all of a sudden it's like zero. Well, think about it. Haha, conferences. Think about it. Why would neon want to gain electrons? Neon's got 10 valence electrons, so like with neon it would be like it just normally has an electron in that last spot. Neon would already have 8 valence electrons. Why would it want to gain one more? Where's it going to put it? It would have to put that electron in like the 3rd energy level. And why would we want to start another energy level? Oh, yeah, the electron affinities for the noble gases are relatively low. In fact, usually reported as 0, because they don't need to gain electrons. They already have full outer shells. So gaining an electron would not make them more stable. And in fact, that's why they're non-reactive for the most part. Mostly non-reactive because they just normally have full outer shells. They don't need to gain any electrons, and they don't need to lose any. And so often when we talk about trends in electron affinity, we don't even count the noble gases. And rarely do we even look at the metals, like the group 1 or group 2 metals. We usually focus just on the non-metals, and that going across as the attraction increases and we get closer and closer to 8 valence electrons, there's more of a chance that we will gain an electron, and when we do, we'll release more energy. But then going down a group, usually we release a little bit less energy, and that's just an attraction issue that, you know, as I go down the group and the electrons are so far from the positive nucleus, I mean, some of these big guys at the bottom, like your antimony and tellurium and iodine, they have a hard time attracting their own electrons. So the chance that they're going to like attract other electrons and gain electrons, it's just not always as likely. And when they do, they're just not going to release as much energy, especially not compared to some of the smaller atoms at the top of the group that have stronger attractions and are more likely to gain the electron and more likely to release energy when the electron is gained.